Hello and welcome to this lecture about spectral index sampling. My name is Trygve Leite-Svalheim and I'm a PhD candidate at the Institute of Theoretical Astrophysics at the University of Oslo. So, as you're all aware at this point, there are several different emission components that contribute to the net signal that we observe on the microwave sky. The most important signal in this part of the electromagnetic spectrum is the cosmic microwave background. But this faraway emission is obscured by a mix of galactic emission, which you can see along the plane here as this red fog. So in this course, the topic, of course, is to properly separate out and categorize each of these individual components. And that's opposed to removing everything that's not the CMB, which would be a whole lot easier. So to do this, we want to know how each of these components behave in frequency domain and how their amplitude and strength varies. So to do this, we observe the sky at many different frequencies. This figure shows all of the Planck observing bands and how the intensity of the foreground signal varies as we move across frequency. From Daniel Herman's lecture, you should already have an idea how some of these components act and why they have this particular behavior. But in this lecture, we'll focus on how to extract their exact shape by making an initial guess using the data that we already know, and then sampling in using Commander to get a physically motivated model and a good representation of the sky. So we see here how the emission on the 30 gigahertz map looks vastly different to that of the 857, and that the lowest amount of emission can be seen at 70 gigahertz. So for just to sum up all the components again quickly, we go through them, starting with thermal dust, which dominates the sky at the high frequencies, which we saw in the last picture, the 857 band, for example. So the reason for the thickness in this plot on the right-hand side here is that we apply different masks when we calculate the amplitude. So this is just the RMS brightness temperature from this map on the left-hand side there, which is the amplitude. So the top value is calculated outside of some mask when the mask is really small, just to remove the very bright galactic plane, which there's a lot of uncertainty tied to. And the bottom line is when applying a larger mask, so that we're looking at the thermal dust up here and down here. So we get a good representation of how it behaves on the full sky. The vertical bars on this plot is also the observing bands for Planck and WMAP and Derby. And we typically model the thermal dust component using a modified blackbody. And that has two free components. That's the beta, which determines the steepness of the fall off here. And there's also the temperature, which determines the peak up here. And this component is polarized, so we also see some of the signal in polarization. Next is the synchrotron component, which we model using a power law. And the steepness is then determined again by a beta parameter. And this component dominates on a very low frequency, so it's high all the way up here and to the left of my pointer here. Adding another component to the mix is the next one is free. And this model is very well defined in physics, and the behavior in frequency space is very similar to that of a power law. So There's this, as you can see in this figure on the right, there's some slight bend at the bottom, but that's an artificial uncertainty that we've added to this plot to emphasize that we don't know much about what it might look like here at the bottom, because this is very weak signal. The final diffuse foreground component is AME for anomalous microwave emission, because its origin isn't completely known, but the consensus is that this is spinning dust grains in the galaxy. And we model this using a template called SP-Dust2, which is generated through simulations. And we shift this template and fit this template back and forth using a new peak parameter, which is a free parameter in our analysis. So lastly, we also mention line emission, such as carbon monoxide. And this can be seen at sharp frequencies at 115 and 230 and 345. So it doesn't have any spectral indices because it doesn't vary in the same way over frequency space. So in total, they make up this whole figure here, which we've extended on the top to show how the synchrotron really dominates on the low frequencies, and that, for example, it's useful for missions like SPAS to get measurements of the synchrotron, which we can extrapolate down to untangle the mess of foregrounds in the very important CMB dominated part of the spectrum here. And the same plot for polarization. So there's less foregrounds here. You can see the spinning dust. We're not really sure to what extent the spinning dust is polarized. So that's why we have an upper boundary here, as opposed to just a sharp line. And we also added the B modes for different values of R. So that we know how strong these would be compared to each of the foregrounds, and how well we must know the foregrounds to actually find these. So we've seen the shape of these models, but mathematically we can express the signal like this. The first one is the CMB, which is a black body with an amplitude that we sample. And the amplitudes aren't important for us in this lecture, because we're just more important for us is the shape of the whole system. So synchrotron is the straight line power law with a beta parameter. Free is this model right here with a electron temperature parameter, which is free, which we sample. And we have the AME, which we shift with the new frequency peak parameter, and the thermal dust, which is the beta parameter for the steepness, and the temperature parameter for the peak, and also point sources, which has this alpha parameter here. So the mixing matrix. You've heard rumors about this before. You might remember from Dr. Watts's lecture on amplitude sampling that this is what we're interested in, especially for spectral index sampling. So we want to know how the amplitude scales a component, or how the amplitude of a component scales from the reference frequency of that component to the different observing bands. So, for example, we extract the thermal dust with a reference frequency of 545, because that's where it's really strong, and it's easy to get a representative view of it. But we want to scale that down to subtract whatever dust is at 70 gigahertz. And the mixing matrix is what helps us do that. So along the columns here, we see all of the different functions that we defined on the last slide. So it scales the amplitude of each of the components into its relative strength at a frequency nu. So that's nu 1, nu 2, and nu n band. So these nus are the different frequencies, and this is the easiest way to represent the mixing matrix. Underneath here, there's a more advanced way, and that's just including a unit conversion factor to convert each of the components to the same unit. And there's also including the frequency dependence through the bandpass for each of these bands, because they usually aren't defined at one single sharp frequency. So we want to get a good grasp of this mixing matrix and how it translates the data, the model properly, so that it matches our data. And we want to know all of these different free parameters, the synchrotron beta, the beta for the dust component, etc., for all of the different ones. And here, one is simply for the CMB component, because we define it in CMB units, so everything is relative to the CMB. So as you know, the full data model used in Commander is a lot more complicated than what we've seen so far. And we sample each of these parameters using separate methods. And for spectral index sampling, which is the topic of this lecture, we have this sampling step right here. So we freeze all the other parameters and we draw beta. So that's the conditional distribution which we sample beta from. So before I go into the details of how to deal with spectral indexes currently, I want to motivate our decisions by talking about what we have done historically. So initially, in the first version of Commander, we analyzed all the data at the same resolution. And this means that we don't care about the beam, and we can solve the system pixel by pixel, and that means that we can actually just apply a simple inversion sampling technique. And that's something that we have to do because the relationship between the spectral indices and the data is linear in the same way that the amplitude is. So we have to do this, which is a bit more computational expensive, but it works very well with this sort of data. But this also means that if we have data sets that have really high resolution for one part of the data set, and another observation that is very low, that we need to downscale the high resolution data to match the weakest link, sort of. So Håvard Ile also talked about this sort of sampling technique in his lectures. Next, in the second version of Commander, we introduced varying resolution. So we introduced different beams for different data sets, and solved all of this in harmonic space instead. But we didn't have a spectral index sampler. So we just used the results in Commander 1 and inserted that into Commander 2, and used that to make our full sky model, and get our final high resolution results. And now in Commander 3, which is the current and latest version, Christian Newton Andersen and I implemented spectral index samplers for temperature and polarization separately. And now we use an MC-MC sampler with a marginal sampling technique for temperature. And we'll get into this. But for the future, who knows? What we're currently using is simple rudimentary methods, but there's still a lot of different types of samplers that could be applied that might be better, such as a Hamiltonian Monte Carlo sampler, for example, which makes better proposals and has a faster and smarter convergence rate. So maybe you will be the one who helps us develop this and contributes to Commander in this way. So there's stuff to do, definitely. Over to Commander 3 and what's currently being done. How do we actually sample this in practice? How is it done in Commander 3? So first we want to create a likelihood that we can work with. What do we want to achieve? And that's what we get from the likelihood. So we want our model to be as close to the observed data as possible. So we obviously want to minimize the data minus model by figuring out the correct parameters for the model. So we define A to be the beam times the mixing matrix given the frequency nu and the beta. So we scale all the amplitudes according to the different spectral parameters. And the full conditional distribution then. So B given all the data and the amplitude, thus becomes, when we apply Bayes' rule like this, we get the likelihood like this times a prior. So this part on the right hand side is a prior, and the data minus minus this A term times the amplitude is this, and that's our likelihood. So how is it done in practice? How do we draw a spectral index value? Well, for each component, and for every spectral index of that component, if it has more than one, we start out with some reasonable guess and sample changes. We propose changes to that value using a Metropolis Hastings sampler. And this makes it sort of a sampler within a sampler, because for each spectral index Gibbs step, we also do several Metropolis Hastings steps. So as we've seen previously, there's several different conditional distributions that we want to draw in, and we want to sample the gain, and we want to sample all of these noise properties and whatever. But within the spectral index sampling step, we have a lot of Metropolis Hastings steps. So to use the spectral index sampler, we start with a value which could, for example, for synchrotron be minus 3.1. So the beta for synchrotron could be minus 3.1. And that's because that's motivated by the literature. So what we know and predict that it might be a good starting point. And we could also start somewhere way off and then see if our system converges on what we already know would be reasonable values. And that might be a good idea if we have time for that. So for each Metropolis Hastings sample, we propose a change to that value, and then we calculate the mixing matrix, the full mixing matrix, to translate to our sky, and we calculate the chi-squared using the likelihood. So we calculate our goodness of fit, and that's the using the likelihood from our last slide there, and we compare it to the previous value, and we see we check if we reject or accept this new beta value, and if it's accepted, we continue using this for the next step, and if not, we just throw it away and then repeat the process. So you can see the algorithm on the right hand side here explicitly written out. So if you want to look closer at that, just pause the video. So these proposals can be very slow. If they're badly tuned, for example, if we make too small changes to this number or even too large changes, it might completely diverge. So we want to tune this sampler, and we do that by running a few rounds and then tuning or figuring out a better step length. And we do that a few times before actually doing the Gibbs run, the Gibbs loop that we want the data from. Now, there are different obstacles that we can face when using these sampling methods. For example, when the amplitude parameter and the spectral indices are very highly correlated, which they often are. In that case, sampling can be very, very slow. So on the right, you see how the conditional, if we sample directly from the conditional, we get a distribution around this point here, which after 100 samples is not what we want. We would like it to be scattered around the true distribution. So we sample the beta given the amplitude A, and if they're highly correlated, it's very slow. So our temperature data has higher signal to noise and higher resolution, so we can actually use more sophisticated methods. So we don't get this correlation here. So for example, when sampling this very highly correlated distribution on the right side, we see that we have to take many steps to make it to the center of the distribution when it's highly correlated, which we don't need to when they're not correlated. So ideally, we would just do a simple diagonal fit, the diagonal guess here. But that's it's not as easy using this method. So instead, we instead of using the regular likelihood we applied in the polarization case, we draw the spectral index values from a marginal distribution instead. So that's for temperature now. So there are some rules when it comes to marginal sampling. So first of all, the same resolution across all data bands. So we have everything at the same smoothing scale. And the pixels must be uncorrelated. And also the beta must vary slowly compared to A. So to get a grasp of what we're actually doing here, we again just to emphasize that the same resolution across all data bands here means that we wouldn't be able to do this in polarization. In Planck, for example, in beyond Planck analysis, the lowest resolution map that we used were WMAP bands at n side 16, while the highest was at 1024. So that means that if we were to apply this method, everything would have to be at n side 16, and we would lose a lot of valuable data. So to understand what we're doing here, we just take the conditional distribution of A and beta, and we apply Bayes' theorem, and we get the likelihood, and then we just use the definition of marginal here, and say that getting, or the likelihood of A and beta is the same as drawing from the marginal distribution of beta, or marginalizing over all of the different values of A, and drawing the amplitude parameter given the beta. So that's still a conditional. And what that looks like is what we see on the right-hand side there. So instead of using the conditional, which is the red line, we sample across the full width of what's possible in beta space. So what that gives us after 100 samples is a much better representation of the true distribution. And the likelihood looks like this. So similar to the one that we had previously with the A's and everything, we now just integrate over all possible amplitudes for the likelihood. And you see that the expression that we get, the final likelihood, is not dependent on A. So that's independent of A. And then the next step is sampling the amplitudes given the beta, which again means that we need to sample the betas before we sample the amplitude. So the resulting maps can look quite different. In many cases, we simply sample one uniform value across the full sky so that we have just one degree of freedom. But when our signal to noise allows it, the results can be a lot more detailed. So, for example, the top right figure here shows that from 2015, the Planck analysis in Commander 1, we sampled pixel by pixel dust temperature, where we see how the structure of the dust component really changes, and how perhaps different types of dust grains contribute differently to the model. And that's very valuable information to have for people who study galactic science. In other cases, for example, where we might have less signal, but we still want to sample the large scale variances across the sky, so not necessarily just pixel to pixel, but just very, um, very coarse spatial variance. We can divide it into regions. So we use what we call region sampling, where essentially the spectral index map is 4 pixels, but these pixels are defined by us. So we sample one value within each of these parts of the sky. So, for example, the fan region in the middle here is particularly interesting when dealing with synchrotron emission. So we say that, okay, we want to sample a different value within this region than on the high latitudes, and, for example, along the galactic plane. So that's better than simply sampling one single value, but it's a compromise when you don't have enough data to do it pixel by pixel. So this GIF also shows how the value fluctuates through many different Gibbs samples. So these are all different maps that come out of varying different parameters in the system, and that many different things go into changing this around. The final result is the figure that you've seen already, but it's a nice place to stop. And we see here how the results shape the sky by this final posterior distribution of all the spectral index parameters. So thank you for listening, and if you have any questions, bring them for the Q&A session. Thank you.